Hi everybody, and welcome to the video for lesson 9.2, which is all about finding the volume of a shape using a cross section. The first thing I'm going to do is sort of explain what this video is all about, but then I want to actually go to a different website and show you a visual of what we're doing here. So I think it'll make what's going on here in these notes make a little bit more sense. So here's the plan. In this lesson, we're going to be learning how to find the volume of a three-dimensional figure using the shape of its cross section. Each 3D figure will have a flat base, and the cross sections, which I'm going to call slices of the figure, will all be the same shape, but will have different sizes depending on their location on the base. So they're going to be the same shape of cross sections, but they're going to have different sizes. I always think about this as being like a loaf of bread. If you look at a loaf of bread, like maybe not like the kind of white bread that you would buy at the store, but like a sourdough bread or something, the base of that bread's going to be flat. And when you slice it, all of the slices are going to be the same shape, but the slices that are closer to the ends of the loaf are going to be smaller than the slices that are in the middle, even though they're the same basic shape. Here's a visual of what's going on here. So I'm going to go to a different website, and I want you to just watch for a second so you can visualize what's happening. So on this website, we're going to start by looking at the graph, and it's shown over here on the left side of the screen. This is the graph of the base of the shape. So in this case, the base of the shape has almost like a flower petal shape bounded by the red and the blue functions. Now I want you to imagine that's laying flat on the table, and you can see that it's laying flat on the table over here on the right side of this website. Now, once we can see that that's laying flat on the table, what we're going to be doing is we're going to be looking at slices if you cut a three-dimensional shape. For the first example here, I want to help you visualize what this would look like if each of those slices was shaped like a square. So here's an example of one slice. We're building a square where the base of the square, the bottom of the square, is on the graph, trapped between the red and the blue functions. And what we're doing here is we're going to go ahead and we're going to build a bunch of those squares. So you can see there's like a bunch of them. And we're going to fill up this entire shape by these squares. Now, each of these squares, each of these slices is very, very thin, like a piece of paper. If you imagine that this is literally as thin as a piece of paper. So when we wanted to find the volume of this shape, one technique for doing that is just to find the area of each of those slices and add them up. Because if you stack enough thin pieces of paper together, you get something that has a thickness, like a pile of papers has a thickness, even though each individual paper is really, really skinny. Now we could make the shapes that we're building here lots of different shapes. So this is an example of what this would look like if there were squares all built on this base. Each of the slices is a square. It's just that the squares at the edges are a little bit smaller than the squares that are in the middle because of where they're located on the base of this figure. What if I change this and I decided to make each of those slices a triangle? Well, you can see here for this equilateral triangle, so all of the sides of this triangle are the same size. Each of those slices is an equilateral triangle shape. It's just that the ones on the edges are very, very small versus the ones in the middle are much bigger because the base shape is wider in the middle. Again, each of these slices is very thin, like a piece of paper, but if you stack enough pieces of paper together, you start to build up a thickness, a pile of papers, and we can use that to find the volume of this shape by just adding up the area of all of those little skinny slices. The last example visual I want to show you is semicircles. So a semicircle is half of a circle. You can imagine that if you kind of drew semicircles on this base, it would look like this. You've got these little tiny semicircles on the edges. You've got the big wide semicircles in the middle. And again, each of those semicircles is really thin. It's sliced like a piece of paper. It's just that if you stack enough of them together, you start to build up a volume. So going back to what we're doing today, here are two visuals for what's going on. In this figure, the shape of the base Sorry, I hate when it shows that little circle thing when I use the mouse. The shape of the base is going to be a circle, Because if you look at sort of what the base shape is here, it's a circular shape. And on that circle base, we're going to be building cross sections that are all shaped like triangles. You can see here that every single cross section is shaped like a triangle. And each of those cross sections is very, very skinny like a piece of paper. In the next picture, you can see again, we have a base that's shaped like a circle. So the base shape here is a circle. And the cross sections here are all going to be shaped like squares. You can see that each cross section, each slice here is shaped like a square. So how do we attack a problem like this? How do we go about actually adding up the area of all those super thin slices to build a volume, a three-dimensional shape? Well, we do that by using an integral, because an integral is how we can add things up. Now, sometimes we're going to graph our base and we're going to find that the cross sections, and this will be told to you in the directions, are perpendicular to the x-axis. Now, remember, the x-axis on a graph is down here at the bottom. So if we are perpendicular to the x-axis and you're looking at your shape, I want you to imagine this is the base of the shape. So we're imagining looking at the shape like a bird's eye view. We're looking at it from above the shape. Each of the cross sections would go vertically, perpendicular to the x-axis, each of those super thin slices. Again, because the thin slices are so thin, it's just going to look like a straight line when you look at it from above. They're just going to be so many of them stacked together that it eventually fills this whole thing in. Now, sometimes in the directions, it'll tell you that your cross sections are perpendicular to the y-axis. And again, it's going to tell you that in the instructions to the problem. We'll look at a couple examples in a second. If that happens, then each of your slices, when you view them from above, is going to go from right to left because it's going to be perpendicular to the y-axis. So once you've identified whether it's perpendicular to the x-axis or perpendicular to the y-axis, that gives you a major clue about how to set up the problem. If your slices are perpendicular to the x-axis, you always set up the integral with respect to x. So perpendicular to the x-axis, everything's going to happen in terms of x in this problem. If the directions say that your cross sections are perpendicular to the y-axis, you are always going to set up this integral with respect to y. So everything in that problem is going to happen in terms of y. You're going to use y values. You should have y's in your equation. You should have dy's, all of that good stuff. So whatever axis you're perpendicular to, it gives you a clue. You have to set up that problem in terms of that variable. Once you've identified that, the way that we set this up and we actually find the volume is we integrate from the beginning a value, which is the beginning x, until the ending value, which in this case is b. And inside of that integral, and this is sort of the new thing, you have to write the area formula in terms of x, dx. So if you're finding the area formula, it might be a square, and the area of a square is side squared. Or it might be a rectangle, in which case it's base times height. And you're going to have to work with some algebra in order to get that formula to use x's and y's, and we'll go through a few examples in a second. And then you would just do the integral. Now, if we want to set it up in terms of y, we would still do an integral. So your volume is going to be the integral from, only because we're in terms of y, it would be from the lowest y value. I'm going to call that e to the highest y value where those graphs intersect. In this case, that would be d. And then inside of there, you would need to put the area formula but this time your formula should be in terms of y. So there should be y's in your equation and then dy. Let's go ahead and take a look at a few examples. So scenario number 1, sometimes they actually give you the area formula you're supposed to use in the instructions. This is the best scenario because you don't have to figure a whole lot out. They just tell you what you're supposed to use. Here's an actual example off of an AP test. Region R is the base of a solid. For this solid, at each x, the cross section perpendicular to the x-axis has an area formula of A of x is equal to 1 over x plus 3. Find the volume. Now, let's just pause for a second. As soon as I see in the instructions we've got cross sections, I'm immediately going to start thinking I need to integrate the area formula. And because it says here that my cross sections are perpendicular to the x-axis, I'm immediately going to think with respect to x. So if I sketch a little visual of what these cross sections would look like on this picture, if this is the base, each cross section would be perpendicular to the x-axis. So from above, it would look like these really thin slices like this. Now, each of those slices has an area of 1 over x plus 3. So step number 1, determine the correct variable. Because it says perpendicular to the x-axis, I'm going to be using x in this problem. Set up your integral is step number 2. My volume is going to be equal to the integral from the beginning x value. Again, this is in terms of x, which in this case would be 0, to the ending x value, which in this case would be 2, of my area formula. Now, they tell me my area formula in this problem, 1 over x plus 3. You just flat out have the formula you're supposed to use, dx. And I've got x's in there already. I don't even need to rearrange the equation. Life is good. From here, we're just going to evaluate the integral. So in order to do that, I would do the antiderivative. The antiderivative of 1 over x plus 3 would just be the natural log of the absolute value of x plus 3 plus c. I'm going to evaluate that between 0 and 2. And so I'm going to have the natural log of the absolute value of 2 plus 3 plus c minus the natural log of the absolute value of 0 plus 3 plus c. Now the c's cancel. 2 plus 3 is 5, so I'm going to have the natural log of 5, and I don't need the absolute value because the absolute value of 5 is just 5, minus 0 plus 3 is 3, so I would have the natural log of 3, and again, I don't need the absolute value because the absolute value of 3 is just 3. And this would be my final answer for this problem. So the volume of this object would be natural log of 5 minus natural log of 3, with whatever that is as a decimal. Again, another example where the area formula is actually given. So this is, again, another actual calculator question from the AP test. A tank has a height of 10 feet. The area of a horizontal cross-section, so you're going to see that word cross-section again, is modeled by the function given. So the area is this equation. They're telling me that in the directions. Based on this model, find the volume. So the first thing is, we're just needing to set up our volume equation. In this case, because the volume is in terms of h, the area is in terms of h, I'm going to do everything in terms of h here. So I'm going to integrate. My volume is going to be the integral from, now it says here in the directions that h, the height of the tank goes up to 10 feet. So if I think about a tank, it would start on the ground, so it'd be 0 feet tall, and it would go all the way up to 10 feet tall. So my bounds would be from 0 to 10. And inside there, I just put my area formula, which in this case is 50.3 divided by e to the 0.2 h plus h dh. Don't forget that whenever you need to evaluate to find a volume, using cross-section, this is always going to be your area formula. Now, you can practice, go ahead and type that in on your calculator, and when you evaluate that, you should be able to get that the volume of this tank would have been 101.325. Now, it does say in the directions here that we want to indicate units of measure. Anytime you find a volume, your units are going to be cubed. So feet cubed, meters cubed. In this case, because the height of the tank is being measured in feet, we would say that the volume of the tank is feet cubed. And this would be your answer. So scenario number 1 is they might actually just say in the directions, here's the area formula for a cross section. Add up all these cross sections to get your volume. Scenario number 2 is you're going to have to come up with an area formula for yourself. So you are going to need to use area formulas that you learned in geometry. Now, you might be a little rusty on these, so I threw some example formulas in here for you. I've got a square, a rectangle, a triangle, an isosceles right triangle, an equilateral triangle, a semicircle. These are all going to be formulas you need to know. So I threw these in the notes for you so that you could review them. Let's go ahead and take a look at an example. So this problem is a very typical AP question. It says, find the volume of a solid whose base is bounded by these functions. So that's telling me how to set up the base. And the x-axis. Each cross section is a square, and each cross section is perpendicular to the x-axis. Step number 1, when you don't have a visual and you're needing to figure this out, and they didn't say anywhere in the directions, here's your area formula. Step number 1 is going to be to actually draw the base and think about the cross sections. So we're going to sketch a picture of f of x equals the square root of x equals 4, and the x-axis. We're bounded by those things. So let's go ahead and do that really quick. So the square root of x graph looks like this. It goes through 0, 0, 1, 1, because the square root of 1 is 1, 2, 3, 4, 4, 2, because the square root of 4 is 2, 5, 6, 7, 8, 9, 3, because the square root of 9 is 3. It kind of curves like this. Now the graph of x equals 4 is just a vertical line. So 1, 2, 3, 4, right here at 4. And the x-axis is my other side of my area. So the part of the graph that is the base of my cross section would be this part of the graph right here. All of my cross sections are being built on this base. Now it says in the directions that my cross sections are also going to be perpendicular to the x-axis. So in this problem, they're all going vertically up and down like this. As soon as I see that my cross sections are perpendicular to the x-axis, my first thought is I'm going to set it up everything here with respect to x. Everything's going to get set up with respect to x. So the next step is figure out an area formula. We know that in order to do our integral, we need to integrate an area formula, but we don't have an area formula here. They didn't tell me one. However, we do know that each of these cross sections is a square. So let's start with that. The area of a square is just the side squared. Whatever side it is, square it. Now in this problem, one side of a square is going to run from the top of this region to the bottom. So in this problem, each side is going to be equal to the distance between the top and the bottom of these functions. The top function is going to be the square root of x, minus the bottom is going to be 0. So the length of one side will be the square root of x, top minus bottom. It's very similar to how we used to find the area of that region. We're just now looking at one side, top minus bottom. If I now take square root of x and I plug it back into this area formula, the area formula that I get is the square root of x squared, which is just x. So now I have an area formula with respect to x. In order to now find the volume, my volume is going to be the integral from my beginning x value, which in this case is 0, up until my end, which is 4. And I'm just going to integrate my area formula, which was just x. When I simplified it, dx. Last but not least, we're going to go ahead and evaluate this integral. Now, the antiderivative of x would be 1/2 x squared plus c. We're going to evaluate that between 0 and 4. If I go ahead and plug in the number 4, I get 1/2 times 16 plus c, minus if I plug in 0, I just get c. The c's cancel, and so I get 8 as my area. Or sorry, my volume. So the volume of this figure is 8. Let's take a look at another example. So this is going to be an example where it says find the volume of a solid. So we're finding a volume whose base is the circle formed by this function and whose cross sections taken perpendicular to the y-axis are semicircles. Now, the first thing that I'm thinking here is if we're perpendicular to the y-axis, everything is going to be with respect to y. So let's keep that in mind as we do this problem. We're going to want y's in everything. The y values, the y's are our variables, everything. Just like before, step number 1 is going to be to sketch a picture of your base. Now, it's telling you that this is the graph of a circle. That was a terrible y-axis. I'm so sorry. So this is going to be the graph of a circle. And because over here it's x squared plus y squared equals 9, the radius of the circle would be the square root of 9, which is just 3. So my radius would be 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. And now you get to see me draw a terrible circle. I apologize. I am not the best circle drawer under best circumstances and certainly not on a computer. Looks kind of like a potato instead of a circle. Okay. So we've got this approximation of a circle. Now our base is going to be the area inside the circle. That's the base of our solid. Now we're building some cross sections on here, and each of the cross sections here is going to be a semicircle shape, and they're going to be perpendicular to the y-axis. So all of my cross sections are going to go like this. Now we don't have an area formula, but we're going to figure one out. So the first thing is each of these cross sections is a semicircle. A semicircle is just half of a regular circle. So to find the area of a semicircle, I would do pi r squared divided by 2. Now, in this case, the radius of my semicircle is only going to be the distance here. So it's going to go from here to here. That's the radius. If I went all the way across, that would be the diameter. That means that I'm going from the right function to the left function. So I'm going to need an equation for the right function. In order to figure out that equation, I'm going to go ahead and solve the original equation, which was x squared plus y squared equals 9, and I'm going to try to get x by itself. So I'm going to have x squared equals 9 minus y squared, and then I'm going to square root, which gives me plus or minus 9 minus y squared. Now that means that this half of the semicircle is the plus, and this half of the semicircle is the minus because it's sort of the negative side for x. So my radius for this problem is going to be right minus left, which is the square root of 9 minus y squared minus 0. The left edge of the radius is right on the y-axis. That would be the equation 0. If I plug that into my area formula, I get pi times the square root of 9 minus y squared over 2, which would just be pi times 9 minus y squared all over 2. So my volume here would be the integral from my lowest y value. Now in this picture, the lowest y value is -3 to my highest y value, which is +3. And inside there, I'm going to put my area formula. Now I'm going to write my area formula a little bit differently, and I'll show you why in a second. I'm going to take the pi over 2 and just put it at the beginning. And I'm going to have 9 minus y squared dy. Now, one of the reasons I put that pi over 2 at the beginning is to make the evaluation process here a little bit easier. Now, for this particular example, we're going to go ahead and do that without a calculator, but because the pi over 2 is just a number, When I evaluate this volume, I'm going to just leave that number on the outside, and I'm going to do this integral, and then I'll just multiply the final result by pi over 2. So in order to do that, I'm going to do the antiderivative. The antiderivative of 9 minus y squared would be 9y minus 1/3 y cubed plus c. And I'm going to evaluate between -3 and 3. Now, if I plug in my numbers, I get pi over 2 times, if I plug in the number 3, I get 27 minus 9 plus c minus, and if I plug in the number -3, I get -27 plus 9 plus c. And then I'm just going to get pi over 2 times 27 plus 27 is 54 minus 9 minus another 9 makes 18, which equals pi over 2 times 36. And if you divide 36 by 2, you get 18 pi. So the volume of this figure would be 18 pi. Okay, let's go ahead and do another example. So now for this one, I'm going to have you actually calculate the final answer on your calculator, because we've done a few examples now where you've gotten to see how we would do this with antiderivatives. In order to make the video just a little bit shorter, we're going to go ahead and use our calculator for the next one. So it says here in the directions, let R be the region bounded by the graphs of x equals y squared and x equals 9. Find the volume of the solid formed if R is the base and the cross sections perpendicular to the x-axis are rectangles. And in that rectangle, the height is 3 times the base. Now, right away, when I see that it says that my cross sections are perpendicular to the x-axis, I'm immediately thinking with respect to x. I'm also thinking we need to try to sketch a picture here. So I'm going to go ahead and sketch a picture of x equals y squared. X equals y squared looks like this. It's just a sideways parabola. So it's just going to be a parabola that's turned sideways because it's the y that is squared and not the x that's squared. Now we're going to 9. 5, 6, 7, 8, 9, which is when we get all the way to here. So I'm so sorry. I ended this a little bit early. Let me just make this a little bit bigger. We're going to where x is 9 right here. Okay. Now this is going to be the base, and on this base, I'm going to build my cross sections, and each of my cross sections is going to be a rectangle. So this is the base of my solid. Okay. Now, because it says in the directions that my cross sections are perpendicular to the x-axis, I know that if I look at it from above, the cross sections are going to look like this. It also says in the directions that it's the shape of the cross section is a rectangle. Now, I happen to know that the area of a rectangle is just base times height, and it says here that the height is going to be 3 times the base. So in this particular problem, my area formula for my rectangle is going to be 3 times b squared. Now, we want to figure out what b is in terms of this graph. The base of each of these rectangles is going to go from the top to the bottom here. So we need to have an equation for the top half of this and the bottom half of this, and everything needs to be in terms of x. In order to figure that out, I'm going to go back to x equals y squared. If I square root both sides, I get y equals plus or minus the square root of x. So the top half of this graph is y equals the square root of x, and the bottom half of this graph is y equals the negative square root of x. That means that each of the bases in this problem is going to be this top function, which is the square root of x, minus the bottom function, which is the negative square root of x, which gives me a total length for the base of 2 square roots of x. And that's what I'm going to plug into this formula. So my area formula is going to be 3 times 2 square roots of x squared. Now, in order to find my volume, I'm going to do the integral from the beginning x, which is 0, to the ending x, which is 9. And I'm going to put my area formula inside of there. So 3 times 2 square roots of x squared. This is in terms of x dx. And when you type that into your calculator, again, this one you can definitely use a calculator for, is going to be 486 as our volume. All right, we have one last example to do, and this is a very typical question. Unfortunately, when I typed this, I made a few typos, so I do want you to change a few things first. The first thing is this exponent should be x squared minus 2x. The minus 2x should not be like x to the 2 minus 2x power. It's just x squared minus 2x. And the second thing is instead of 6.4, this should be 6.5. I apologize. It was just a typo when I typed this. It says here, R and S are going to be the regions bounded by these graphs of f and g as shown in the figure. And then it says that S is the base of a solid. So region S is the base of the solid. So this part of the graph right here is going to be the base of our shape, our three-dimensional shape. And in this solid, each of the cross sections is perpendicular to the x-axis and it is a square. Now, immediately upon seeing that, I'm going to think to myself, okay, if my cross sections are perpendicular to the x-axis, everything is going to be with respect to x, which makes sense. If you look at the setup of these equations here, everything is in terms of x. And when I visualize that, it's going to go from top to bottom like this. Each of those slices is going to go from top to bottom. We want to find the volume of the solid. So in order to find the volume of a solid, we need to start by finding the area of one cross section. Now, the area of a square is the side squared. In this case, one side of this graph is going to go from here to here. In order to identify which function is which, you can definitely graph these on your calculator. I'm going to tell you right now that this graph right here is your f of x graph, and this graph right here is your g of x graph. So in this case, the f of x is actually the top of this graph. So it would be f of x is the top minus g of x is the bottom for each cross section, which means my area formula would be f of x minus g of x squared. You do not, on the AP test, have to write out the entire equation, which is really convenient if there are really long equations like this, as long as you identify them by the names given in the problem. So if it says f of x and g of x in the problem, and you show your work and you write f of x and g of x for everything, that is a totally acceptable way to show your work here without having to write down those long equations every single time. Now my volume here is going to be the integral from, and that's when you realize, oh my goodness, I don't know this intersection point. So on my calculator, I'm going to find that point, and it should be 1.032832, comma 2.401108. Now that means I'm going to use this x value and this ending x value, 1.032832 to 2. And I'm going to put my area formula inside, which is f of x minus g of x squared dx. Now, this is a calculator question. So as soon as you figure that out, you just type in all of this stuff into your calculator. Of course, you have to actually type in your f of x equation and your g of x equation to evaluate this. Be really careful. I would definitely try that to make sure I can type everything in properly. And at the end, you should get that your volume is 1.283. All right, that's it for today's video. Thank you guys so much for watching. I hope you have a great day. And don't forget to try your practice problems to make sure you understand this concept.